Okay, so we can start the session. So we try to be as much in time. Well, thank you everyone to be here. So this DM5 parallelization, which is beyond the lambda CDM, will be related to either phenomenology and observation aspects of dark matter, mainly from particle dark matter, either candidates that go from fuzzy dark matter, fermionic dark matter, cold dark matter as well, with different candidates, but mainly related to, as I said, to observations, to the phenomenology, and to simulations, as well as some talks will be dedicated mainly in the second part of the sessions, either tomorrow, today and tomorrow, about more theoretical or model building, or some theories related to dark matter halos. So yeah, phenomenology. So the idea is to try to link all together and to see what we can learn out of this with the latest results and observations. And well, so let me present then Pietro. So if you want to start your camera.
Yeah.
So Pietro Bergamini is the first speaker of today. And he will, if you can start to share slides, it's okay.
Okay, probably now you can see my screen. Okay.
Yeah, so he will talk about excess of small-scale gravitational lens observing galaxy clusters, a very nice result that I took attention, I think, of many people. Indeed, I was happy to see this result when it just appeared, and I was trying to go through the paper, but it's good now to have Pietro here from INAF. You can start.
Okay. So first of all, I would like to thank the organizer for the opportunity of presenting our work during this event. And what I'm going to present is a work that was published on Science last year, and that was the result of a collaboration of all these scientists. Also, Claudio and Gabriel are here in the audience. And especially also, this work was published thanks to the contribution of Massimo Meneghetti, that is the first author of the paper. And essentially, what we found in our study is a discrepancy between the mass distribution and the radial distribution of the sabelo in observed galaxy cluster respect to the sabelo predicted by the cosmological simulations. So this is essentially the outline of my talk. So I will start with a brief introduction on galaxy cluster and strong gravitational lensing. Then I will move describing the data that we use to develop a lens model that is the source of information for the mass distribution of the observed clusters. And then I will describe the so-called high precision strong lensing models that are the state-of-the-art model for the cluster of galaxies. And then I will show the result reported in the science paper. So let me start with the cluster of galaxies. So the cluster of galaxies are the largest gravitational bound structure in the universe, and about 85–90% of their mass is in the form of dark matter. So it is obvious that these astronomical objects are the perfect natural laboratories if you want to study the physical properties, for example, of the dark matter particle, such as its collisionless nature, for example. And since the cluster of galaxies are massive, because they have masses of about 10 to the 15 solar masses, they usually act also as powerful gravitational lenses. So in gravitational lensing, essentially, if you are observing a faraway galaxies, and you are on the Earth here, so here there is an observer, here a galaxy, and if between you and the galaxy there is a mass, such as the large mass of a galaxy cluster, the light rays coming from the background galaxies can be curved, and you can observe distorted and sometimes magnified images of the same background galaxies inside the field of a cluster. So this is a real cluster. This is called MEC 0416, is one of the clusters considered in our study. And here in green, you can see the multiple images that we identified in the field of view of this cluster. These are 182 multiple images. And here on this corner, you can see also the magnification maps that is obtained from the lens model for this cluster. And the red line here is the so-called critical line, and is essentially the line over which the magnification of the multiple images tend to diverge. Sometimes also the galaxy can produce strong lensing. In fact, if you have a galaxy that is massive enough and compact enough, this galaxy can produce the formation of multiple images around its own critical line. So this is the critical line of galaxies. And here you can see 4 images of the same background source that is formed essentially from 2 knots of star formation. When this kind of event happens, we call this event a galaxy-galaxy strong lensing system. Now, as I said 2 slides ago, the mask can curve a light rays and produce multiple images of a same background galaxies. But if we reverse the problem, it is also true that we can use the position of the multiple images to accurately predict the mass distribution of a cluster member galaxies and of a galaxy clusters. So this is the aim of the lens models. And obviously, to produce accurate lens model, you need also you have to meet these requirements. So, for example, you need accurate position of a large sample of multiple images. You need to know the redshift or distances between the lens and the sources that you are observing. And you also need, according to the identification of the cluster galaxies, that are the sub-halo component of your cluster. And if you want to further improve the lens model, it is useful also to use other sources of information that can trace the mass. For example, in the model that I will show you in a moment, we implemented a methodology to include the measured stellar velocity dispersion of a cluster member galaxy to better constrain the sub-halo distribution of the clusters. So, as I said, to meet all of these requirements, we need high-quality photometric and spectroscopic data. And the data, in our case, for our model, comes from 2 large surveys, and in particular, this 25 clusters in green were observed during the so-called CLASH survey. CLASH means Cluster Lensing and Supernova Survey with the Hubble Space Telescope, and consists in a survey that observed 25 massive galaxy clusters in this redshift range, and observed this cluster in 16 Hubble bands from the UV to the near infrared. Instead, these 6 clusters here were observed in another survey that is called the Hubble Frontier Field Program, that consists in ultra-deep Hubble observation in 7 bands that are reported in this table. So, among all these clusters that were observed during these 2 surveys, we selected the 11 clusters that have an accurate strong lensing model. And in particular, we identified 3 samples of clusters that differs for the quality, if you want, of a lensing model that they have. So we have a reference sample for our analysis that essentially counts 3 clusters, for which we have the state-of-the-art lens models that include also the information coming from the stellar kinematic of the cluster member galaxies. The second sample is the so-called public Hubble Frontier Field cluster sample, and count 4 clusters, 4 Hubble Frontier Field clusters, whose lens models were developed by other group, and these models are public in the online. And then we have a third sample of galaxy clusters. It consists in 4 clash clusters, and the lens model were created by Gabriel Camigna, that is here in the audience. For what concerns the spectroscopic data, our data come mainly from 2 main instruments. For example, during the CLASH VLT survey, essentially this spectroscopic survey consists in VMOS observation of 13 CLASH clusters that provide us hundreds of cluster member galaxies, so allow identification of 100 cluster member galaxies at tens of multiple images per cluster. And more recently, Several clusters were also observed with the Muse integral field spectrograph, that is an integral field spectrograph at the VLT telescope, that allow us to increase by a large factor the number of detected multiple images in the core of a cluster of galaxies. Just to give you an example, here you can see the improvement thanks to Muse from the initial set of multiple images identified inside this cluster that are 30. So the Clash VLT survey allow us to identify 30 multiple images inside this cluster. But recently, last year, thanks to a new Muse deep observation, we were able to identify up to 182 multiple images. And multiple images for the lens model means the constraint to the mass. So we have also a great improvement in the lensing models. So let me spend just a couple of slides in explaining how we can create a state-of-the-art lensing model for the clusters. So first of all, we use a parametric software to create a lens model. This means the software is called Lens Tool, and in parametric modeling, it is usual to divide the mass distribution of a cluster into the sum of several different mass components. So we have a first component here that essentially account for the large cluster scale halo that are made essentially of dark matter that creates the cluster. Then you have a second term here that is a shear term that can, for example, account for the presence of mass structure in the outer region of the cluster. Then you have a third term that is a gas term, and this term can be, for example, fitted from the X-ray observation of the cluster, such as the Chandra X-ray observations. And finally, we have the substructure term. So inside this term here, you have a contribution to the lens model of all the galaxies. And the galaxies are usually parameterized using the so-called DPIE profile. So this is essentially an isothermal profile with a flat core and a truncation radius for the mass. And for the galaxy, it is usual to take the core radius of this mass profile equal to 0 or very, very small, and to scale the central velocity dispersion that is here and the truncation radius according to scalar relations which scale the value of these two parameters with the luminosity of the galaxies. Now, why we use scaling relation? Because essentially the constraint that we have, that correspond to the number of multiple images that we have, are not enough to constrain all the parameters of a single galaxies. So using the scaling relation, essentially you are able to reduce the number of free parameters in your lens model. Now, in my model that, as I said, correspond to the reference sample that we use in our study, we use the measure velocity dispersion of a cluster member galaxy, a stellar velocity dispersion, to constrain or to fit the parameter of the scaling relation used to parameterize the galaxy inside the lensing model. So here, the dots, this is a plot that shows essentially the velocity dispersion as a function of the magnitude of the galaxies. The dots here are the measured velocity dispersions of the galaxies. And here in green, you see the relation that we fit and that we use as a prior in our lens model. This is a spectrum, a fitted spectrum to determine the velocity dispersion of this particular galaxy inside this aperture. And for what concerns the constraint to a lens model, so let me stop a moment with this video. The constraint to the lens model are, as I said, the position of the observed multiple images. So the goal of Lens Tool in the process of the optimization is to minimize the distance between the observed and model predicted multiple images. Just to give you an idea, here you have a figure that shows, for example, the projected mass distribution of a cluster that I showed you a moment before, that is max 0416. Here you have the magnification map, and in red you have the observed position of the multiple images. In green you have the predicted position of the images by the lens model. And here you have the displacements along the y and x axis of the displacement between the observed again and the predicted position of the multiple images. So during a Lens Tool run, essentially you minimize this t-square and you find the best model that can reproduce the position of your observed images. And at the end of this process, you have a perfectly and accurate reconstruction of the mass distribution for your cluster. So this is essentially the best fit solution, and the error in determining the position of the images is just 0.4 arcseconds. And this is just another animation that show you the cluster. This is another cluster, it's 1206, and superimposed to this real image, you see the reconstruction using Lens tool. Now I spent just a few words in describing the dataset of simulation that we use for our comparison between observation and simulation. So we use the Dianoga simulation that are essentially consist in a sample of 25 massive galaxy cluster. The good match the observed cluster in terms of mass concentration, in terms of also phase mass densities, and also in the ellipticity of the core part of the cluster. This Dianoga simulation also include all the physical processes that shape the mass distribution of a cluster and of a cluster subhalos, such as, for example, the AGN feedback, the stellar feedbacks, the gas cooling. 5 minutes. Ah, okay. And okay, so I probably have to go faster, but this is the first comparison that we did between the observed cluster subhalos and the subhalos in the simulated dataset. So in this plot here, you see the cumulative mass function of the subhalo predicted by the simulation in gray. So the gray lines are the predicted subhalo mass function from the simulation, and while the colored line are the subhalos mass function derived from the lens model for the reference sample of clusters. And you see immediately that the two results are in very good agreement. However, what we found is a discrepancy in the so-called galaxy-galaxy strong lensing probability. So let me explain better this concept.
Sorry, you have 8 minutes. Sorry, it was my mistake.
Ah, okay. You have more time. Okay, so as I said, we observe this mismatch in this quantity. Just to recap the main concept. So a galaxy-galaxy strong lensing system is essentially a strong lensing event on a scale of a single galaxy. So you have a galaxy that can split a single source in multiple images. And obviously, to do this event, this galaxy have to have enough mass and enough compactness also. And if you want to estimate the probability to observe such kind of event, there is a way, and essentially what we have to do is to map the critical lines of the system. So this is the critical line of the system that I showed you a moment ago. These are the, in blue are the surface brightness contour of the multiple images. And if you map back the critical lines to a source plane, you obtain the so-called caustic lines. So the caustic line that is here is very, very small, so I need a zoom in. So this caustic line corresponds to the critical line that is here, that is mapped to the source plane using the Lens equation. And to have a strong lensing event by a single galaxy, what you need is a source that is inside the caustic line that corresponds to the critical line of a galaxy. So essentially, the area contained inside that caustic line correspond to the cross-section of observed for this galaxy, this galaxy-galaxy strong lensing event. So if you want to estimate the probability to observe a galaxy-galaxy strong lensing event, you have to follow a chain of steps. The first step, you have to identify the secondary critical line, so the critical line associated to the galaxies on the lens plane. Then you have to use the Lens equation to map these critical lines at a given redshift on the source plane. Then you have to measure the area contained inside the caustic line of the galaxies. So in this way, you can determine the cross-section of the galaxies. And to obtain a probability, you have to sum all the cross-section of a strong lens event and divide it by the area that are you probing with, for example, your Hubble Space Telescope, mapped on the source plane. So this is the probability to observe a galaxy-galaxy strong lensing event. If you plot this probability as a function of the redshift, you obtain this curve. So the curve grows across the redshift, and the reason for this growth is quite obvious, is related to the fact that critical line and caustic line tend to increase the size with the redshift, and so does also the probability to observe a galaxy-galaxy strong lensing event. This line is the line corresponding to the reference sample containing these three clusters. And from this line, you can also try to predict, for example, the expected observed number of galaxy-galaxy strong lensing event. For example, it's just an integration of a probability, essentially. And in this plot here, you see the number of expected galaxy-galaxy strong lensing event as a function of a limiting magnitude that you can detect with your instrument. For example, with the Hubble Space Telescope, you can reach this magnitude here, so you expect about 3 galaxy-galaxy strong lensing events in this cluster, which is called MAX 1206. And in fact, we found exactly 3 events for this cluster. These are the 3 events. This is a sort of Einstein ring. These are 3 images of a single source around this galaxy, and this is an Einstein cross that is not visible in the HST image, but is visible in from the Muse data cube because it's a Lyman alpha emission. Okay, so now the problem, we start to have problem, because if we compare this curve here with the simulation, so in this plot, I'm also plotting the result from the other 2 samples of strong lensing model and galaxy cluster. And if we compare this curve with the simulation, we notice it an order of magnitude mismatch. And so the question now is, what is going on? And to explain this mismatch, we have to look to other 2 functions that describe the cluster member galaxies. So here on the left, you see the velocity, the circular velocity function. So a circular velocity is defined in this way as a function of the mass of a subhalos, and you see that the observed circular velocity function is different, is larger, the value of the circular velocity are large in the observed halo respect to the halo inside the simulation. And since the circular velocity is defined in this way, this means that at a given mass, the observed subhalo are more compact than the simulated analogs. And instead here, you see the cumulative radial distribution of the subhalos. And if you look to these 2 functions, this is the simulation, these are the observations, you immediately observe that the observed subhalo tend to be more concentrated toward the center of the cluster respect to the halo inside the simulation. So just to summarize, we can say that at a given mass, the observed subhalo are stronger lenses because they are more compact and of the simulated analog, and are also more concentrated toward the cluster center, where the main critical line of the cluster resides. And so thus the internal structure and the radial distribution function of the subhalo in numerical cosmological simulation are different from those in real cluster. And this is essentially the mismatch that we see in our work. So there are several possible, this is my last slide. So there are several possible explanations for this discrepancy. We try to resolve most of them. So with red crosses, I just marked the possibility that we rule out. And so at the end, what we stress is that probably this mismatch that we observe is due to something, for example, like a missed piece of physics inside the simulation, or can also be due to a wrong dramatic prescription, for example, a wrong assumption like the assumption of the collisionless nature of a dramatic particle. So I can stop here. If you have questions, probably I just can leave a slide here.
Yeah, okay, thank you. Pietro, thank you a lot for this very, very nice talk with the huge work you have done. Okay, so yes, if everyone has questions, please raise the hand or just turn on camera. Okay, so in the meantime, would like to make a comment. So what I have, after reading this work, what I have found very, very interesting is that it seems that, meaning the hierarchical structure formation, for example, in lambda cold dark matter or even in lambda WDM, when matrix clamping, I mean, there is no enough, so even cold dark matter that generate Cusp or more clampy distribution respect to, for example, warm dark matter, is not even possible to, or you show that by an order of magnitude, it's not possible to reproduce this difference in dispersions, velocities, or in kinematics. And to me, I mean, it seems that it may be is suggesting a different way of hierarchical clustering. Well, the hierarchy probably remains, but the way it relaxes the halo and the way it gets in a steady state, it may be suggesting a new way of relaxation. So this is, I think, I found very interesting. This it's a hint to me.
For the moment, in reality, we don't have an explanation for these discrepancies. So we are trying several possibilities, let's say, for example, other models or also for the simulated data set. But it's still a work in progress. So probably in the near future, we have more results and we can try to shed more light on this problem.
Mark, Rodrigo, good. So, yeah.
So thank you, Pietro. That was really, really interesting. I was just wondering, so to what extent are you limited by your parametric model? I mean, could it be that by adding more terms to the parametric model, things would change, or how does that work out?
Yeah, obviously, the problem is that at the moment, the parametric model outperform the free-form model for the clustering for what concerns, for example, the prediction of the correct observed sets of multiple images. So for the moment, the best that we can do is to use this parametric model to determine the mass distribution of the clusters. And obviously, it is also true that, for example, to describe a galaxy, we are assuming a profile. So this so-called DPA's profile, that is, as I said, an isothermal profile with without a core, essentially, in our case. But I think that this is not the problem. Also because, in reality, we tried also to use, for example, the forward modeling to test the validity of our models. And for example, here probably a plot somewhere, probably on the science paper. However, our model are able to reproduce also, for example, the shape and the surface brightness of all the images inside the cluster field of view. So this means essentially that your mass distribution is quite similar to the mass distribution of a real cluster. And so I don't know in reality. So I think that it's not a problem of the lens model. I'm quite sure that it's more a problem in the simulation. But
Pietro, sorry, I don't know if someone else has a question or a comment. I would like to make a very short one so we can skip to the next speaker. But can you say at which sigma you can exclude that this is due to purely baryonic physics, baryonic component of the cluster?
In reality, I have not a number here. Probably Massimo did something to estimate this possibility. But because you mean that, for example,
it would be nice to know if this excess has to be mainly due to dark matter, or has to be mainly due to some new baryonics.
Yeah. In reality, for example, for what concern, for example, also physical processes that are well known, for example, the feedbacks from stars or ADN.
Yeah.
So we know that, for example, removing the ADN feedback, we can partially solve this discrepancy. However, it is also true that your simulation have also to predict the other observables, such as, for example, the stellar distribution inside the galaxy, and also, all the processes, the physical processes that affect also other fields of the astrophysics. So the point for me is that if you have a simulation with a different, for example, recipe for the baryons, or that can explain this mismatch, probably there is something of wrong in other, for example, in the stellar distribution or in other observables.
Okay. Thanks a lot, Pietro. And okay, then we will have more time in the discussion session, so we should keep to the next speaker.
Yeah, absolutely.
Okay, so we have Mark Lovell, if you can. Good.
Oops, no, this is not PowerPoint, so it doesn't do that. Okay, see cursor, see slides.
So it's a pleasure to present Mark Lovell from University of Iceland. And well, he will talk about probing the nature of dark matter with Milky Way subhalos. Please go ahead.
Okay. Thanks to the organizers for inviting me. I should say I'm unfortunately not going to be able to join you for the discussion at the end of this session because I've got my vaccine at 10 o'clock local time. I'll be at the discussion tomorrow afternoon, but I may or may not have had a reaction, and you'll get to find out whether I've had a reaction to it, which will be very exciting. Okay, so I was given a fairly broad scope by the organizers as to what I wanted to talk about today. So I've actually picked 3 projects, one of which is slightly older than the others, one of which is to do with gravithermal collapse in self-interacting dark matter models, which was published recently by my master student. Some work on gaps and streams, which will be quite close to what Rodrigo Bass is going to talk about tomorrow, which is currently under review. And also some slightly older work on X-ray decay signals in galaxy clusters, just to make sure that everybody remembers what that is ahead of next year. Okay, so self-interacting dark matter and gravithermal collapse. So as you have, so in a self-interacting dark matter model where the dark matter particles are, say, exchanging dark photons or something, and they're able to bounce off one another. When you have lots of collisions in the core center, in the center of the halo, this can cause the creation of a core. But if you have sufficiently large number of interactions over the history of the universe in this particular cluster, in this particular dark matter halo, it can throw out so much material from the middle that it's no longer supported, in which case you have this gravithermal catastrophe where everything starts charging together to the center. And then whereas before you had something that was cored and was much less dense than CDM, as I'm going to show you here, instead you get something that is much more dense than CDM. This has several applications, one of which could be to explain black hole seeds. So if you've got all this material flowing to the center of a dark matter halo, it can form a black hole. But what we're interested in today is explaining the, or finding a way to explain the density of ultra-faint dwarf galaxies in the case that you were trying to work with an SIDM model and you find that these halos are too dense to be fit by SIDM. So on the right-hand side here, I've got a plot of the cross-section as a function of the relative velocity of particles that are doing an interaction. So the simplest model you can think of is something like the green or the blue, where you just have 1 centimeter squared per gram or 10 centimeters squared per gram interaction cross-section. But if you have a high cross-section at large velocities, then you run foul of constraints from galaxy clusters that constrain the reaction rate that constrain the cross section to be less than, or no more than, I think 3 centimeters squared absolute maximum, could well be a bit lower than that by now. And instead, you can have these velocity dependent models, such as this red model that we see here, which is the main one we're going to be considering today, is where you have very little cross section at large radii in order to avoid problems with the with clusters, but then at low velocities, which is the relative velocities that you get in the center of, say, Milky Way satellite halos, you get a much larger velocity, you get a much larger cross section, and this is able to give you this collapse. So here's a picture of the 6 simulations that we used in this study, although I'm only really going to discuss the 2 on the left-hand side. So this is taking a Milky Way halo analog, AQA3, its figures are on the left-hand side, and just showing you what these halos look like. You can see that in this SIDM term model with this large cross-section at large velocities, the halo looks more spherical than in the other cases, but otherwise they look remarkably similar, until I try to bring out what the densities of these subhalos are like, where if I ask, well, what if I make the densities, what if I just pick out the densest peaks in CDM, the 2% densest peaks, draw a red circle around them, and see how many similar red circles of the same density I find in the other runs. And this is what we get. So in CDM, we have 62 of these peaks. In SIDM 10, where you have lots of these cores, you only have 13 peaks. In the VD100 model, we have 120. So this is your first piece of evidence that you've had dark matter collapsing to form these gravithermally collapsed subhalos. We can show this here in a more quantitative way by looking at the peak of the circular velocity profile. So this is in the CDM run. On the bottom, we've got the value of that peak, Vmax, which is often used as a proxy for mass. And on the y-axis, you've got Rmax, which is roughly the radius, or you could think of it as a concentration, where lower Rmaxes are more concentrated. So in CDM, you have this particular relation between the two. But when instead we use VD100 and I put that on top of this, you'll be able to see that we have this extra population of objects in the bottom right-hand corner that is much denser at a fixed Vmax than you would see in CDM. It's a separate population, obviously taking some of the objects from CDM and they are shifting to the bottom and to the right. I should say that the dashed line is the resolution, the horizontal dashed line is the resolution limit of the simulation, so you can't trust the actual value of Rmax at Vmax in that case, but it's enough to say that this object is clearly much denser than you have in CDM, even if the details are unavailable to us. So I can show you some examples of this here. If I just take halos that have a measured Vmax of 25 to 35 kilometers per second, and put these in a plot here. So I can do it first for CDM, and you get this characteristic shape where you have some low velocity at the halo center. I should say the dotted line is again this resolution limit, so you have to be careful interpreting what happens there. And as you move to the right-hand side, you get these characteristic peaks in CDM. Then in SIDM, we have 2 very distinct populations in the pink and the red. So starting with the red, you can convince yourself that actually some of these circular velocity curves in the VD100 track what's going on in the CDM, which is evidence that you're actually picking out the same objects here. And so is this somebody else making sound there somewhere? Thanks. And whereas in CDM, you have this gradual drop off in circular velocity. In VD100, in these in the red objects, you get this drop off, which is much steeper than in CDM, and this is actually a sign that you've got a core. But in addition to this, you've also got the pink ones, which are actually the remnants of less massive objects that have undergone this collapse. And there you see, instead, you have this rapidly rising rotation curve up to where the resolution limits your ability to say anything. I don't have the plot here, but we actually measured in this simulation the density profile, and we showed that the density profile slope is -3 all the way up to this resolution limit. So finally, for this section, I can show you why this is important. So this is comparing observations from a previous paper that we did using the same simulations with my boss here, Jesus Zavala. And here you have the observations, which are these mass size relation values for observed galaxies in the points. And what we'd argue here is that if you look in the outskirts of the halos, and also to those that have a radius of around 0.3 kiloparsecs, then you could argue that you would like to have chord halos in order to match those objects. But to get to the objects that are within 0.1 kiloparsecs, which here we do using extrapolation, then if you want to do this, then you need to have these gravithermally collapsed subhalos. So that's what the real interest is in having this sort of model, that you can have your LCDM model that can give you cores in some circumstances where you think there ought to be cores, and also it can give you gravithermally collapsed objects. Next topic is slight change into subhalo distribution in gaps and streams, which Rodrigo is going to talk about tomorrow. Just a very brief introduction. You have an object, a stellar object that falls into your Milky Way halo. It gets stripped by the gravitational field of the Milky Way, leaves behind a stream of stars, and there's the possibility that one of the many dark subhalos in CDM could rip a hole, and then this would leave a mark. You can go and detect that. You can go and count the number of gaps, or do statistics on the gaps, and then work out how many dark subhalos you think there are. And based on that, you can say, well, either CDM is correct, or maybe if you don't find those gaps, then perhaps WDM is what you're looking for. But what I particularly wanted to know is whether or not you would get the same effect from the, so when people have often looked at this in the past, they have compared the subhalo mass function, which is what we're interested in, across the whole halo rather than just the inner 20 to 30 kiloparsecs where you can measure the, where you can actually measure streams. So I wanted to know whether or not the population of subhalos in CDM and WDM is the same in the halo center as it is in the halo as a whole. So to do this, we use the COCO simulations, which is this big circular or spherical n-body simulation. There's no hydro in here, just in case you're the referee who's particularly keen on this. So it's 28 megaparsecs. We've got about 28 candidate host halos that could be Milky Way analogs, just according to a host halo mass. I should say we only use isolated Milky Way analogs here, so we're neglecting any possible impact from M31. And there are two copies of this, one of which is CDM, which you see here with its large amount of small scale structure. And then this is the WDM one. I scoop between those, so you can see that the large scale structure is preserved, and on the small scales you lose material. And this is what happens when you zoom in on one of our objects. You see that in CDM you have lots of these small objects, when in WDM you just have these filaments full of these spurious subhalos that are an artifact of the simulation. So what do we get? So what I'm going to do is I'm going to calculate just count the number of objects within a given mass bin in subhalo mass within 40 kiloparsecs of the halo center and the halo as a whole. And that's what we have here. So if we start off looking at the central panel, at the bottom panel here, we have in the mass range of 10 to the 7 to 10 to the 8 solar masses. If you just look at the solid curves, the solid boxes, that shows you the distribution across these 24 halos as to how many, as to the ratio of the number of objects in WDM to CDM, first within 300 kiloparsecs, which is the whole halo, which is in blue, and then the inner region, which is in orange. And what you see here is that in the halo as a whole, the number of objects in this regime is suppressed by a factor of 90%. So when you get 10% in WDM as you would in CDM, whereas in the central region, you have a much larger variety. and it's actually more like 30%. And we show in the paper that this is due to many of the objects in the halo center being the remnants of large objects that fell in, and the difference between the two models is is smaller for large halos than it is for much smaller ones. And so most of these objects are objects that have fallen and been stripped. And then in the dashed line, I just discussed differences between two effects of if you have the just the fact that you have fewer objects falling in CDM versus WDM. On the other hand, that you have more stripping in WDM because the halos are less concentrated. And so what we're showing just between the solid and the dashed is that both of these things play a role. And you can see something similar in the 10 to the 8 to 10 to the 9 box, except that the difference between WDM and CDM is that bit smaller again. So the main takeaway from this point is that the abundance of subhalos in the center of the Milky Way halo is actually more similar between CDM and WDM than if you looked at the halo as a whole. And we show in the paper that this is due to dynamical friction of large objects falling to the halo center. And then you can take an interest in the concentration of these perturbers. So if you look at 300 kiloparsecs regime and you do a mass size relation, which is effectively mass concentration, and you look at the pink and the gray, so the top two lines, this is a prediction for the mass concentration relation just for objects when they'd first fallen in, okay? So this is a limiting case before you've had any stripping. The black and the red, so the bottom two, are instead a prediction for what you would have in the halo center based on considerations around steepening of the halo, removing the outer layers of the halo. But again, this doesn't have a full hydrodynamical astrophysics treatment, so it's very much a first guess. But the main thing you would take from this is that there is a clear difference between what you would get for objects based on what they've done when they've fallen in versus those that are in the halo center, with the latter being much more concentrated. And this could be relevant for saying, well, if you do find an object and it's at some particular impact parameter radius, so gap between the stream and the between the stream and the halo, you would have to get well below 2 kiloparsecs most of the time to see a difference in CDM and WDM in the halo center where the streams are. Whereas if you looked at the halo as a whole, you might have thought that you might start to see these differences even within 4 kiloparsecs. Okay, how much time have I got? Carlos? You muted, are you?
Sorry, you have 3 minutes.
Okay, that's enough. Thanks. So finally, I want to go back to some older work, but nevertheless, I will always want to take the opportunity to come back to this because this is one possible really good way to, or perhaps the most compelling way to actually get a detection of a dark matter particle within the next 2 years. So this is the famous / infamous 3.5 keV line. It's been claimed in clusters, and the Milky Way center and M31 and other people have claimed to rule it out in stacks of galaxies at 15 sigma. So this has been much discussed, and there seems to be mostly arguments about what the right way is to model the background. But there's one particularly really nice opportunity coming up to get a definitive measurement of whether or not this line can be detected in clusters of galaxies, and if it is, whether or not it is from dark matter or from an astrophysical line based on its width. Because if you have an astrophysical line, then you expect the width to be less than 200 kilometers per second. But dark matter can't cool in the way that baryons can, which means that you're stuck with velocity dispersion of the material when it fell in. And this is a lot higher. So if you see a really broad line, then you're able to say, oh, I'm quite sure that this is dark matter. Particularly nice that it could be a stellar neutrino, which can fix lots of other problems, but that's not something you're going to be able to learn from this, just to say whether or not, if you see a line, what it is. So we made some very specific predictions here using the Sea Eagle simulations, which is a series of 30 simulations of clusters of galaxies. And what we're hoping is that the CRISM experiment, which is going to launch in 2022, provisionally, maybe it'll be later by now. You'll find out on Saturday morning there's a talk about this. And just using the position or the distance from us and to the Perseus cluster and the instrument, and do mock observations, at least in theory space, of the cluster. And based on the whole series of different sight lines, you can get an estimate for what you expect the width of the line to be. And so from this paper, we found that you should get something in the range of 500 to 800 kilometers per second, which is a lot broader than the atomic emission lines, which, as I said, should be lower than 200 kilometers per second, but also narrower than the velocity dispersion of the member galaxies, which have fallen in later. So if you just looked at the velocity of the galaxies that are falling in, and you measure their velocity, then you would think something like 1,200 kilometers per second. But luckily, we don't have to wait that long to get the detection, we hope. Also made predictions for some other clusters, and Coma is pretty much the same as Perseus. So these are my conclusions. So I've shown how that if you have a self-interacting dark matter model, you can explain both the cores of cored objects and the high densities of uncored objects simultaneously. Otherwise, SIDM is possibly not viable. That in WDM, the structure and abundance of objects in the regime where you would have clusters, where you'd have gaps in stream, be able to measure gaps in streams is much smaller between CDM and WDM than the halo as a whole. And also that we could possibly detect dark matter in decay and X-ray experiments within the next 2 years. Thank you.
Okay, Mark, thanks a lot for your talk, for all these nice works. And well, this open the questions, comments. Rodrigo.
So lovely talk, very interesting, Mark. Just a little question. So am I right in understanding then that the way to go about checking CDM, WDM might be through so looking at the the production of gaps in streams as a function of distance from the Milky Way then?
I expect, or another way of putting it is that as you are able to go further out from the halo center, the better you'll be able to do. So you might have noticed that I actually cheated a little bit in my results here, in that I quoted halos that are out, and I used halo data that's out to 50 kiloparsecs rather than within 30, which is just in order to get enough objects. So it could even be the difference between CDM and WDM is smaller than what I claim here. So what the baryons are going to do when you do that, put those in, is a really big open question. But yes, it is the case that the further out you go, the easier it is to make a distinction between them. But otherwise, you would jump to other observables entirely, probably still gravitational lensing.
Thanks.
Okay, anyone else? Another question? I have a question. Yes, so the first part of your talk, gravothermal collapse. So have you checked the collapse numerically only? This is, it recalled me the typical collapse of globular clusters I mean, this gravothermal collapse, have you checked numerically, or have you done, it was possible to do a more analytical or analysis like with the caloric curves, checking the collapse? Or
well, you could say we just did it effectively at the empirical level, just to say that.
What is the criterion?
So I guess that there wasn't one criteria. If you were going to do a criterion, at least empirically, you would look at the red curve that I have here, and you would effectively draw a line in between those two. The one thing we did do is in the paper we have the Vmax Rmax relations at redshift 1, okay? And you're able to then track the same subhalo across time, and you can see how at redshift 1 you have the same Vmax Rmax relations in VD100 and in CDM. And then as time progresses, the CDM objects tend to move to the bottom left in this graph, if anything, as they get stripped, whereas in VD100 they move to the bottom right as they collapse. So it's not necessarily some first principles calculation that shows that these collapse. It's more the case that nobody
so
had ever run the simulation.
Collapse. Okay, maybe the name collapse is a bit misleading. I mean, in the sense of because it resembles the so-called gravothermal collapse or of typical classical systems, like occurs in globular clusters, for example, that it occurs this gravothermal catastrophe or collapse. But in this case, it's just this relation that get clampier, and you stop at some point. But okay, so it's not we are not using a theoretical or criterion that says, okay, until this threshold it should collapse. So
no, there's no threshold put in. The only input to the simulation that's different to CDM is the cross section velocity curve. And so you just put that in, and then you wait for several months, because this is a very intensive simulation to do. And then at the end, you get these collapsed objects that nobody's seen in a simulation before.
Okay. Okay, thank you. So we have any other question? We have still some few minutes. Okay, thanks a lot then, Mark. And we keep to the next speaker. Juba, if you want to start sharing.
Hello, everyone. So
Okay.
I would like to.
Yes, sorry, Dhruva. So I present Dhruva Dutta Chaudhuri from Yale. He will talk about the random motion of nuclear objects in a fuzzy dark matter halo. And well, you can start, please.
Yeah, thanks. So hello, everyone. I would like to start by thanking the organizers for giving me the opportunity to talk in this meeting. And my talk today is going to be on the random motion of nuclear objects in a fuzzy dark matter halo. And this talk is going to be based on the following paper, which is available on the archive. So let me begin with a brief introduction to fuzzy dark matter. So fuzzy dark matter is an alternative to cold dark matter, and it consists of ultralight bosons. The occupation numbers of the bosonic density field are very large, and this implies that it behaves as a classical field, and it can be characterized as a wave function psi that obeys the Schrodinger-Poisson equation. So the first equation here is the well-known Schrodinger equation. MB is the boson mass, and phi is the potential, which is self-consistently sourced from the mass density via the Poisson equation. Now, for a boson mass of about 10 to the power minus 22 electron volts, it turns out that the de Broglie wavelength is of the order of a few kiloparsecs. And we know that wave-like behavior is exhibited on scales comparable to the de Broglie wavelength. Therefore, if dark matter is made up of ultralight bosons, then it will have interesting implications on galactic scales, or scale on kiloparsec scales. On scales much larger than de Broglie wavelength, it behaves as cold dark matter. So the next natural question arises is, why are we interested in fuzzy dark matter? And the reasoning is mainly twofold. First, it can resolve some of the well-known small-scale problems in cold dark matter. For example, the missing satellites problem, which is highlighted here. So as we all know, missing satellites problem goes as the Milky Way halo has way more subhalos, as shown in a simulation here, than the observed satellite galaxies around the Milky Way. And the way fuzzy dark matter can potentially resolve this problem is that uncertainty principle suppresses structure formation on scales below the de Broglie wavelength. Therefore, we will have fewer subhalos than in cold dark matter, and therefore it could be a possible solution. Another well-known problem is the core cusp problem, and this has to do with the fact that CDM predicts cusp NFW halos, whereas at least observations of at least some galaxies tend to favor cored profiles. So the data here is for 2 galaxies from the THINK survey, and it is shown that a Burkett core profile is a better fit to the rotation curve data than a cuspy profile. Now, the way fuzzy dark matter solves this is that the ground state solution of the Schrodinger-Poisson equation, it consists of a constant density core. Therefore, fuzzy dark matter halos naturally have cored density profiles. Now, of course, within the cold dark matter paradigm, these problems can be solved by invoking baryonic feedback. And so that leads to the second motivation for studying fuzzy dark matter, and that has to do with the so far null detection of WIMPs, or weakly interacting massive particles. So with this brief introduction, I will jump right into our work. And in our work, we simulate a fuzzy dark matter halo in isolation with a Schrodinger-Poisson solver. The initial conditions for this halo, by which I mean the wave function at t equal to 0, that is extracted from the z equal to 0 snapshot of a cosmological FDM simulation, Scheib et al. 2014. And we use the Gamer2 code, which is also by Scheib. The total halo mass of this halo is 6.6 times 10 to the power 9 solar masses, and the boson mass is 8 times 10 to the power minus 23 electron volts. So when I click next, you're going to see a movie of this halo. So what I'll show is the evolution, the time evolution of the projected density of the halo. So let's take a while to look at this movie, and then I'll discuss in more detail some of the interesting properties of this halo. Okay. So what I'm showing here is the density profile of this halo at a particular instant of time. And what is shown on the left is the 2D, so it's a 2D slice, the density in a 2D slice, and which cuts through the maximally dense cell in the simulation. And this red central nugget, this is the ground state of the Schrodinger-Poisson equation, and this is what is normally called the soliton. And outside the soliton, you have density fluctuations throughout the halo, and these density fluctuations arise from the interference between the excited states of the Schrodinger-Poisson equation. What is shown on the right with magenta is the azimuthally average density profile for this, this particular time instant. And notice that there's a core in this density profile, which I was talking about earlier. And the blue dashed curve, that is the universal solitonic profile, which is given by this relation. And so we adjust rho 0 so that it matches the density of the maximally dense cell in our simulation. And RC is obtained using the scaling relation. So solitonic profiles follow the scaling relation. And RC is known as the core radius of the soliton. What is shown with the black curve is the NFW profile, the universal NFW profile. And we adjust rho S and RS so that we can roughly match the normalization and the slope of the magenta profile in the halo outskirts. The green vertical line here that indicates the soliton radius, which we define as roughly the radius where the density profile transitions from being soliton-like to NFW-like. Now, the soliton also interacts with the excited states, and as a result of which the soliton undergoes temporal oscillations in density. So what is shown here with the different green curves is the density profile of the halo at different time instants. So you see that there are oscillations in the soliton and also outside the soliton in the halo. So basically the halo also responds to the oscillating soliton. But still the profile in the inner region is soliton-like and the outer profile is NFW-like. What is shown here is the oscillations in the peak density. The peak density oscillates by about a factor of 2. And what we show below is the power spectrum of this oscillation. So these oscillations exhibit a very characteristic frequency, and most of the power is in this sort of orange region, which is very sharp. Now, the interactions of the soliton with the halo, or the interference of the soliton with the excited states, also causes the soliton to undergo a confined random walk with respect to the halo center of mass. So what is shown in the top 4 panels here is the projected density of the halo in a small region of 5 × 5 kiloparsec centered on the center of mass of the entire halo. And the center of mass is sort of indicated by this white crosshair. And then you also see the soliton, and we define the center of the soliton as the maximally dense cell. And you can see that the soliton is offset from the halo center of mass, and the offset changes with time. And what is shown in the bottom panel is the evolution of this offset, the distance of the soliton center from the center of mass of the total system as a function of time. And this displacement is roughly of the order of the soliton radius. The soliton radius, if you remember, was 2 kiloparsecs. Now, besides density, another interesting property of a dark matter halo is its velocity dispersion profile. So for our system, we can define the velocity for each cell if we know the phase of the wave function. So given theta, the phase of the wave function, the velocity of each cell is given as h cut over boson mass times the gradient of theta. And then what we can do is we can divide the halo in somehow, like, I can't see my cursor. Sorry, yeah. So we can divide the halo in radial shells, and in each shell, we can find the dispersion of the cells along X, Y, Z, and then average them in quadrature to get the halo dispersion, the 1D halo dispersion. And this can be done for different time steps. And because the density profile oscillates, the dispersion profile will also have some oscillations. And so what we show in magenta is the median over different snapshots over a 10 gigayear time period, and the 1 sigma variance with respect to that median, or the 16 to 84 percentiles. Now, so the velocity dispersion is close to 0 in the central region, and then it sort of rises and then falls again. Now, what you can also do is you can use the time average density profile as input and use the spherical Jeans equation, spherical isotropic Jeans equation, to get the Jeans dispersion. And the Jeans dispersion is shown with this orange line. And so we see that the Jeans dispersion is higher than the actual dispersion of the halo. And this has to do with the fact that the self-gravity in an FDM halo is balanced by both random motion and quantum pressure. And therefore, if you're solving Jeans equation, then we are basically finding an effective dispersion. which is higher than the actual dispersion due to random motion. But what is very interesting is that if you take this Jeans dispersion and divide it by square root of 2, you get the blue curve, and the blue curve and the magenta curve overlap very nicely outside the soliton, and which basically means that outside the soliton, the energy density at a particular radius that has about equal contribution from classical kinetic energy and quantum kinetic energy. Classical kinetic energy and quantum energy. And so this was also shown in previous simulations. For example, Mock et al. 2017 showed this, but in a different context. They were using soliton-soliton merger simulations, and they found the same result. So another thing that you can do is you can characterize the density fluctuations. So at a particular radius and time, we can look at the overt density with respect to overt density at location theta phi, and then take the spherical harmonics expansion of that overt density, get the multiple components, and then write the variance in delta as a sum of the multiple components. So the total power at a particular L is given by this, which is summed over the different M modes. And the angular wave number L is related to the radius R and the size of the fluctuations, the diameter, basically, by this relation. So what is shown on the left is at a particular radius, we plot this total power at a particular L as a function of L. And this is the time averaged power. So we do this for different time steps and then average it. And then we sum over the powers at different L to also get the time averaged variance. So there are several things that can be noted from this figure, several interesting things. One is that the soliton core, so inside the core radius, that is roughly spherically symmetric. So you have very little variance, also very little power at different L's. Now, as you go from the core radius to the soliton radius, you start becoming aspherical. And that has to do with the fact that this is not a naked soliton. The soliton and the halo are interacting with each other. Now, what you can also do is you can find the L at a given radius. You can find the L that has the maximum power. And that is shown by this pink line. And you can also plot the relation between L and R for fixed diameters D. Those are these cyan lines for soliton size, 1.5 times soliton radius and 2 times soliton radius. So basically we find that the characteristic size of the density fluctuations, they increase from about soliton size to 2 times the soliton size. And we can also compare this with analytic formalisms. So there have been a few papers which have shown that outside the soliton, sufficiently far away from the soliton, the density fluctuations in an FDM halo, they can be envisioned as a sea of quasi-particles with effective mass given by M effective equal to rho times some constant F and lambda dB to the power whole Q, where lambda dB is the de Broglie wavelength defined in terms of the Jeans dispersion. Now, this effective mass can be converted to effective diameter, and that effective diameter can be converted to an RL relation using this, and that is what is shown with the magenta line here. So roughly, the analytic predictions outside the soliton, it is consistent with what we find in our simulations. And the variance, so as you cross the soliton, the variance quickly becomes unity and stays unity throughout. So basically that means you have ordered unity fluctuations everywhere in the halo. Now, so we saw that we have a soliton which is moving around with respect to the halo center of mass. It is oscillating, and then you have
5 minutes, Dhruva. Sorry.
So, and you also have this density fluctuations in the halo, and these will. So if you place any object at the center of the soliton, then that cannot remain there. Because of these gravitational potential fluctuations, the object will diffuse outwards over time. And as the object will start to diffuse, it will also feel a mass-dependent force of dynamical friction, which is induced by the wake created by the motion of the object. And therefore, there's going to be some frictional cooling. And basically, if you have a nuclear object, by which I mean a supermassive black hole or a nuclear star cluster that was initially at the soliton center, it will continue its outward motion until this diffusive heating and frictional cooling balance one another. So this movie shows a particular realization for a 10 to the power 5 solar mass object. A 10 to the power 5 solar mass object was placed at the center of the soliton and at rest with respect to it. And then we let the simulation evolve, and the particle gradually moves outwards over time. So in orange here, the particle motion with respect to the halo center of mass is shown. In green, the motion with respect to the soliton is shown. And the blue line shows the soliton motion with respect to the halo center of mass. Now, the image here, that is always centered on the instantaneous soliton. That's why you don't see the soliton move, but you can see the particle gradually diffusing outwards. And we model them as point particles. So in the interest of time, I'll skip this slide and directly move to here. So now we can make statistical ensembles of different masses. So we did 10 to the power 5, 10 to the power 6, 5 times 10 to the power 6, and 10 to the power 7. Typical nuclear star clusters or black hole masses would lie here. And for each of these statistical ensembles, we can see how the median radius is evolving and how the 16 to 84th percentiles vary. And we can also compare that with massless particles. So in each panel, the curves in cyan show the evolution for massless particles. So what we find is for 10 to the power 5 and 10 to the power 6 solar mass particles, the evolution is essentially the same as massless particles, which basically means that they feel very little dynamical friction, at least within the runtime of the simulations. And they were basically evolving as massless particles. And as we increase the mass, we see reduced outward diffusion, and the behavior is no longer the same as massless particles. That means dynamical friction is becoming important. And for 10 to the 7 solar mass particles, we see a rough sort of balance and in an ensemble average sense between cooling and heating. So you see sort of a stalling behavior around the core radius after about 1 gigayear. So to summarize, we make testable predictions for the dynamics of nuclear objects, for example, central black holes or nuclear star clusters in an FDM halo. For the adopted halo and boson mass, the one that we have simulated, low mass objects, by which I mean about 0.3% less than the soliton mass, they are typically ejected out of the soliton in a few gigayear. More massive objects, they remain largely confined to the soliton due to dynamical friction. And future work will make testable predictions for different halo and boson masses, with the hope that we can use spatial offsets of AGNs and nuclear star clusters from the centers of their host galaxies to constrain the boson mass. So thank you. I'll take questions.
Thank you very much, Dhruva, for your talk, for this nice work about fuzzy dark matter. Is there any questions? We have 5 minutes or a bit more. Pietro?
Yeah, I have a question that is more a curiosity, because you mentioned that the fuzzy dark matter can resolve a missing satellite problem, right?
Sorry?
You mentioned that the fuzzy dark matter can resolve a missing satellite problem, right?
Yes.
So my curiosity is because in cluster of galaxies, we observe exactly the opposite problem. So we have a lack of substructure respect to the simulations.
Right.
So do you know if there is a way to explain both the...
So I'm not sure. So, I mean, fuzzy dark matter, I think, will always suppress structure formation compared to CDM. So therefore, yeah, so your result is very interesting and very surprising. So I don't know how to explain that in the context of fuzzy dark matter. So what you find is that you have more subhalos than theoretically predicted, right?
More low mass subhalo
more low mass subhalos than predicted in cold dark matter.
Exactly.
Yeah, so I don't think that can be explained with fuzzy dark matter.
Okay, thanks a lot.
Yes, so I would like to make a comment related to these questions, but so Pietro, but the conclusion, the interpretation, I mean, either you have more substructure towards the center with respect to simulation, but you could there is also place to be more concentration of dark matter, right? Respect to the simulations or not.
In reality, we have both the problems. So it's a problem of the concentration, but it's also a problem of a number
of substructure.
Yeah.
No, well, regarding the concentration, I think fuzzy dark matter, or I mean, more generally, models of dark matter, collisionless dark matter, which include the quantum nature of the particles as fuzzy dark matter or fermionic dark matter, they may, to me at least, it may be a hope, and I think it would be very interesting to test these models. I think the possibilities to implement these new profiles, which are concentrated towards the center, either fuzzy or fermions, to see if this nucleation or this concentration can help in any way, in some way, to release that tension. But
okay, thanks a lot.
Okay. Is there any other? Indeed, we should at some point collaborate, but
yeah, sure.
Is there any other question related to Dhruva's talk? Yes. Okay. Rodrigo?
So well, it's super interesting. I was just wondering though, in terms of the because it seems to me that one can use streams as well to check this idea, right? And effectively, on what sort of timescales are there, substantial variations at the distances where we find streams, which is, I don't know, between 10 and 50 kiloparsecs. And on what, so these things will have scales of dwarf galaxies, right? The variations. But I guess what we need to do in order to test this is to see how nearby orbits diverge.
Right. Yeah.
And so I guess my question is, on what timescale are there these substantial variations? So I don't know, something like 10, 20% variations in local density. Not in the solitonic core, but in the outskirts of the galaxies.
So basically what you're asking is if you have a circular orbit, sort of maybe at a radius far away from the soliton, then on what time scales is that orbit going to, like...
a nearby object's going to diverge, right?
Yeah. Yeah. So that depends on so it's basically it has to do with so it will be the local relaxation time scale. And the relaxation time scale you can derive from the fuzzy dark matter particle mass. It will depend on the local density. It will also depend on the fuzzy dark matter particle mass. And so off the top of my head, I don't know what the relaxation time scales are, but it is calculable. You can calculate that. And you can calculate that by using just analytic prescription, so that the quasi-particle formalism that I was talking about, you can use that quasi-particle formalism to calculate those relaxation timescales.
Okay, that'll be really interesting. Thanks.
Okay, well, let's thanks Dhruva again, and we entered the coffee break with a couple of minutes delay, but it's okay. So we have more than time for questions on all these speakers. So let's please be here again at 11:05 for the talk of Pierre-Henri. And well, thanks a lot, and see you in 15 minutes, 10 minutes more or less, 12 minutes, 10 minutes, sorry. Como qua. Muchas. Okay, so we should continue. Shabani.
Hello.
Pierre,
Yes.
are you there?
Can you
Yes.
hear me? Yeah. Okay.
Yes, we can hear you well.
And
Okay, we start the second. Yes. ¿Son de audio o no? No hay, no.
No. What up?
Sorry. Can you start to share slides, Pierre?
how do I do?
Yes, you should have a green box in the bottom, share slides, and it should appear the option of your different windows, and you should choose your PDF or PowerPoint.
So I click on share screen.
Yes, and then it should open different windows, but you should have already
Desktop.
open in the desktop or wherever. You should have open your presentation, so you choose from this.
Okay. Then I have a screen security and confidentiality.
Well, you should skip that. Or
Okay.
press.
And can you see my screen now?
Not yet. Nope.
Probably
Shabani, what are you using? Mac?
just to allow the computer screen from the security setting in the Mac.
So let's see. Gregory, are you there?
Yes, I am.
Good. So do you know if there is maybe something related with the right to share screen? No, he's okay, right, with that?
Yes, but if he's using Mac, I think he has to set up some permissions and probably even reboot or quit and come back again. I always have these troubles with Mac, people with presentations with Mac. So I don't know what, there are some permissions requested by the system.
Are you using Mac, Pierre?
Yes, yes, a MacBook.
Okay.
Enregistrement d'écran.
Yeah, probably you have to go to the system preferences and then security and privacy. And then...
Is it working now?
Yeah.
Okay, perfect. Okay, so can you see my screen?
Yes, and I am here as well, Remo Ruffini. Look forward to hear your talk.
Could you please try to share your webcam as well?
Yes, if you can share your webcam, Pierre, it's okay.
Oh, well, it's not maybe for the questions, but...
Okay, no worries. Okay, so it's really a pleasure to present Pierre-Henri Chabani from Université Paul Sabatier. I want to say that it's really a pleasure of presenting him, having read his works from several years already, and so I'm very happy to present Pierre. So you can start, please.
Okay, so I will talk about phase transitions in the self-gravitating Fermi gas. And I will not go into technical details, but I will try to make a sort of short history of the subject, going from white dwarfs, neutron stars, up to dark matter fermion balls and black holes. Oh, sorry. Okay. So I just have one slide about the formalism to fix the main idea. So what we want to do is to determine the statistical equilibrium state of a gas of self-gravitating fermions in Newtonian gravity or general relativity. And to that purpose, we will use a maximum entropy principle. So we will look for the most probable distribution of self-gravitating fermions at equilibrium. So it leads to an optimization problem. In the microcanonical ensemble, where the energy is fixed, we have to maximize the Fermi-Dirac entropy at fixed energy and particle number. And in the canonical ensemble, where we assume that the system is in contact with a heat bath fixing the temperature, T, we have to minimize the free energy, E minus Ts, at fixed particle number. So if we write the first variation for the microcanonical ensemble, we have a variational problem like this one, where beta and alpha are the Lagrange multipliers associated with the conservation of energy and particle number. And beta is the inverse temperature as measured by an observer at infinity. And alpha is the chemical potential divided by kBT. And at the level of the first variation, we have exactly the same variational problem in the canonical ensemble, which means that the equilibrium state and the caloric curve will be the same in the microcanonical and canonical ensemble. Only the stability of the system, which is related to the second order variation of entropy of free energy, may be different in the microcanonical and canonical ensemble. So these variational principles are very nice because they yield all the equations that we need. So they determine the distribution function, which in the present case is the Fermi-Dirac distribution function. From the distribution function, we can get the equation of state. This equation or this variational principle also imply the Oppenheimer-Volkoff equations, which state the condition of hydrostatic equilibrium in general relativity. And they also imply the Tolman-Klein relations, which relate the temperature and the chemical potential to the metric. So we can solve these equations, and then we can obtain the caloric curve, which relates the temperature to the energy. So in the following, I will plot for convenience the inverse temperature, beta, with respect to minus the energy, where the energy here is the binding energy because it reduces to the usual energy in the Newtonian limit. Okay, so let us first consider self-gravitating fermions at 0 temperature. So the self-gravitating Fermi gas appeared in astrophysics in connection with white dwarf stars when Fowler in 1926 realized that white dwarf stars owe their stability to the quantum pressure of the electron gas, which is due to the Pauli exclusion principle. And the mass-radius relation of non-relativistic white dwarf stars was determined by Stoner, Milne, and Chandrasekhar. It is reproduced here, and you see that the radius of the star decreases as the mass increases. If we take special relativity into account, there will be a maximum mass, which was discovered by Anderson, Stoner, Chandrasekhar, and Landau. And the complete mass-radius relationship was computed by Chandrasekhar in 1935. And you see that for large mass, it starts to depart from the non-relativistic mass-radius relationship. And at some maximum mass, which is known now as the Chandrasekhar limit, the radius goes to 0, and there is no equilibrium state above that mass. If we consider now general relativistic fermions, they were introduced in connection with the study of neutron stars. So in that case, the mass-radius relationship has a spiral structure. So again, there is a maximum mass that was discovered by Oppenheimer and Volkoff in 1939, and which appears now at a finite radius. So there is no equilibrium state above this maximum mass, and the system will collapse towards the black hole. We can also show that the series of equilibria becomes unstable at the maximum mass, the first turning point of mass, and that a new mode of instability is lost at each subsequent turning point of mass. Let us now consider classical non-relativistic particles at non-zero temperature. So the statistical mechanics of self-gravitating systems confined within a spherical box of radius r was studied by Antonov and Lindenbell and Wood in the 1960s. So we have to put the system in a box, otherwise the system would completely evaporate in infinitely large time, and there would be no equilibrium state. So they consider this model in relation with globular clusters. And in that case, the caloric curve, which gives the inverse temperature beta as a function of minus the total energy, has a spiral structure. So in the canonical ensemble, where the control parameter is the temperature, you see that there is no equilibrium state below a critical temperature corresponding to this turning point of temperature. And in that case, the system will undergo an isothermal collapse leading to a Dirac peak. We can also show in the canonical ensemble that the series of equilibria becomes unstable at the first turning point of temperature, and that a new mode of instability occurs at each subsequent turning point of temperature. In the microcanonical ensemble, where the control parameter is the energy, you see that there is no equilibrium state below a critical energy corresponding to this turning point. And in that case, the system undergoes what Lindenbell and Wood have called the gravothermal catastrophe, and it leads typically to a binary star surrounded by a hot halo. So again, in the microcanonical ensemble, we can show that the series of equilibria becomes unstable at the first turning point of energy, and that a new mode of instability is lost at each subsequent turning point of energy. So you see that there is a region of negative specific heats between CE and MCE, which is stable in the microcanonical ensemble and unstable in the canonical ensemble. And indeed, we know that negative specific heats are allowed in the microcanonical ensemble, but they are not allowed in general in the canonical ensemble. So this is a region of ensembles in equivalence, which is stable. The equilibrium states are stable at fixed energy, but they are not stable at fixed temperature. And inequivalence of statistical ensembles may happen for systems with long-range interactions, like self-gravitating systems. Let us now consider the radiation that would be so intense that self-gravity, in the sense of general relativity, has to be taken into account. So we consider the statistical mechanics of the self-gravitating blackbody radiation, a sort of photon star, confined within a cavity in general relativity. So in that case, the caloric curve has again the form of a spiral, but you see that it is reversed with respect to the previous one. So I will call this one the cold spiral because the instability occurs at low temperature and low energy. And I will call this one the hot spiral because instabilities occurs at high temperature and high energy. Indeed, you can see that there is no equilibrium state, this time above a maximum temperature corresponding to that turning point. And there is no equilibrium state above a maximum mass or a maximum mass energy above that corresponding to that turning point. And in that case, the system collapses and forms a black hole. Let us now consider classical particles at non-zero temperature in general relativity. So in that case, the caloric curve forms a double spiral. So the cold spiral on the right can be seen as a relativistic generalization of the spiral that I showed previously for globular clusters. And the hot spiral on the left is relatively similar to the hot spiral of the self-gravitating radiation in the sense that it corresponds to ultra-relativistic configuration. But for classical particles in general relativity, these two spirals occur on the same caloric curve. So in that case, there is no equilibrium state below a critical temperature or above a critical temperature in the canonical ensemble, and there is no equilibrium state below a critical energy or above a maximum energy in the microcanonical ensemble. Another thing is that the caloric curve depends on a control parameter, mu, which is proportional to the ratio of the number of particles divided by the size of the system. So if mu, or the number of particles, is relatively small, the two spirals are relatively well separated. But if we increase mu, they will start to come into contact. At some point, they will merge. And even at some point, for a maximum particle number, they will disappear. And in that case, there won't be any equilibrium state, whatever the value of energy and whatever the value of temperature. Let us now consider non-relativistic self-gravitating fermions at non-zero temperature. So in that case, the caloric curve depends on a parameter mu, which is given by this expression, and which typically measures the size of the system. So small values of mu will correspond to small systems, and large value of mu's will correspond to large systems. So when mu is very large, so the system is very large and quantum mechanic effects are unimportant, we recover the classical spiral that I showed previously. But when we decrease mu, when we decrease the size of the system and quantum mechanics come into play, we see that the effect of quantum mechanics is to unwind the spiral. And depending on the value of mu, or depending on the size of the system, we will have different shapes, which will give rise to different types of phase transitions. So let us first consider the case of small systems. So in that case, the caloric curve has an N-shaped structure like that. You see that in the microcanonical ensemble, where the control parameter is the energy, the curve is unevalued. There is only one equilibrium state for each energy, and it can be shown that this equilibrium is stable. It corresponds to a maximum entropy state. So all the series of equilibria, in that case, in the microcanonical ensemble, is stable. In particular, you see that there is a region of negative specific heats, and this region of negative specific heats is stable in the microcanonical ensemble. If we now consider the canonical ensemble, the control parameter is the temperature, and you see that now the curve is multi-valued in the sense that for a given value of temperature, you can have several equilibrium states. And this will lead to phase transitions. So I will not go into too much detail, but I explain just the basics. So the curve, the branch on the left here corresponds to gaseous states. And you see that when the temperature decreases, at some point, a turning point of temperature, the gaseous branch disappears. And in that case, the system will collapse. It will undergo an isothermal collapse until quantum mechanics come into play through the Pauli exclusion principle. And in that case, we will form a structure with a core halo structure made of a quantum core, a fermion ball, surrounded by a small halo. So this will form the condensed branch with this core halo structure. If we now increase the temperature, at some critical temperature, the condensed branch disappears. And in that case, the system undergoes an explosion, reverse to the collapse from the gaseous phase to the condensed phase. From the condensed phase to the gaseous phase. So in this manner, we can describe a sort of hysteresis in the canonical ensemble. We could expect the occurrence of a first order phase transition at this transition temperature, Tt, at which the gaseous phase and the condensed phase has the same free energy. But it can be shown that for systems with long-range interaction like gravity, the metastable state here that are local but not global minima of free energy in the present case are very robust, very long-lived, because their lifetime scales like the exponential of the number of particles, which is very large in general in self-gravitating systems. So in practice, this first order phase transition will not take place. And when we reduce the temperature, the system will remain on the metastable branch until the point of collapse here. Let us now consider larger systems. So in that case, the caloric curve has a Z-shaped structure that I call a dinosaur's neck, because I found on the web that it looks like a dinosaur like that. It's very impressive. And we have, in that case, the following. So for large system now, you can see that in the microcanonical ensemble, we can have, the curve is multi-valued in the sense that we can have several equilibrium states for the same value of energy. So this will give rise to microcanonical phase transitions. So the upper branch corresponds to the gaseous branch. So if we decrease the energy, at some point corresponding to the turning point of energy, the equilibrium state will become unstable. In that case, the system will undergo a collapse, the gravothermal catastrophe, until quantum effects for fermions come into play through the Pauli exclusion principle. And in that case, the system will reach an equilibrium state on the condensed branch, which is a quantum core, a fermion ball, surrounded by an atmosphere, an isothermal atmosphere. Again, if we increase the energy, the system remains on the condensed branch until this critical energy corresponds to this turning point of energy, at which it will undergo an explosion from the condensed phase to the gaseous phase. So now we can describe an hysteresis in the microcanonical ensemble. Again, we could expect a first order microcanonical phase transition at this transition energy, where the gaseous solution and the condensed solution have the same entropy. But for the same reason as before, in practice, it will not take place because the metastable state on the gaseous branch have a very long lifetime. So in practice, they are stable. So I have drawn here different density profiles corresponding to the solutions that I showed previously. So here you have the gaseous solution of the gaseous branch, so which corresponds to
5 minutes, Pierre.
Sorry?
5 minutes left.
Okay, perfect. Corresponding to the upper branch here. So quantum mechanics is negligible for the gaseous solution. And here you have the condensed solution with a core halo structure, which are made of a fermion ball, a quantum core, surrounded by an atmosphere, an isothermal atmosphere, which is similar to the one of the gaseous solution. And if we increase again the size of the system, we consider very large system, the phenomenology remains the same, except that the system undergoes several rotations before unwinding. So we have a more complex structure like that, but the phenomenology of the phase transition remains the same as before. Let us now consider general relativistic fermions at non-zero temperature. So in that case, the caloric curve depends on two parameters, the particle number and the size of the system. If we consider relatively small systems, the caloric curve has an N-shaped structure as before, but the precise form of the curve will depend whether the number of particles is below or above the Oppenheimer-Volkoff limit. So if we are below the Oppenheimer-Volkoff limit, typically the things are the same as the one I presented previously for non-relativistic systems. But if we are above the Oppenheimer-Volkoff limit, there will be a new turning point of temperature, a second one here, and the caloric curve will have this form. Similarly, if we consider larger systems, if the number of particles is below the Oppenheimer-Volkoff limit, we have the dinosaur's neck as before. But if the particle number is above the Oppenheimer-Volkoff limit, there is another turning point of energy here in the caloric curve that we had not for non-relativistic systems. And this is interesting because in that case, the system can undergo two types of collapse. First, a gravothermal catastrophe from the gaseous branch to the condensed branch, stopped by quantum mechanics and leading to a fermion ball surrounding by a halo. But if the energy keeps decreasing, at some point the condensed branch disappears, and in that case, nothing can prevent the collapse of the system. Quantum mechanics is not strong enough, and the system is expected to form a black hole. So the result that I showed previously were valid for the ordinary Fermi-Dirac distribution function. But in that case, I had to put the system within a box in order to have a finite mass and have a well-defined equilibrium state. Of course, the box is an artifice, and it's not very physical, but we can avoid the box, and we can solve the maximum mass problem by using the fermionic King model instead of the usual Fermi-Dirac model, which is a quantum generalization of the classical King model, which was introduced for globular clusters. So the classical King model takes into account effects of evaporation and leads to a distribution function similar to the Boltzmann distribution, but with a finite mass. Similarly, the fermionic King model takes into account evaporation effects, but also quantum mechanics effect, and it leads distribution functions with a finite mass. So now we can redo all the previous analyses in terms of these more general models. So the phenomenology will be exactly the same as before, but the shape of the caloric curve will be a little bit different. So for example, if we consider non-relativistic classical King model, so the caloric curve as before presents a spiral structure leading to an isothermal collapse in the canonical ensemble and to a gravothermal catastrophe in the microcanonical ensemble. So this is as before, except that, as you can see, the shape of the caloric curve has changed. Similarly, if we consider non-relativistic fermionic King model, again, we see that the spiral unwinds, and in that case, the gravothermal catastrophe can be stopped by quantum mechanics. So this corresponds to the dinosaur's neck that I showed previously. But as you can see, in the framework of the fermionic King model, the shape of the caloric curve has changed a little bit, although the phenomenology of the collapse and explosion remain the same. We can also plot the corresponding density profile. So they have a structure similar to the one I showed previously. For example, the gaseous phase are represented here, and the condensed solutions have a core halo structure with a quantum core, a fermion ball, and an isothermal halo. The main difference with the previous case in the box model is that, as you can see, because of tidal effects, the density goes to 0 at a finite radius. So the mass is finite, and we don't have to put the system within a box. And finally, I want to mention the recent work of Argel and collaborators, who consider the general relativistic fermionic King model, and who recovered the two turning points of energy that I showed previously in the case of box confined system, the one corresponding to the gravothermal catastrophe, and the one leading to a formation of a supermassive black hole. So I will conclude here and mention two papers with a lot of reference in them. And thank you for your attention.
Okay, Pierre, thanks a lot for very clear, very detailed presentation. And well, this is a place for open questions, discussion, comments are welcome. Have a couple of minutes. If not, I have a comment. Okay, so regarding this situation where you have phase space density with cutoff, the fermionic King, and in general relativity. So the stability, could you say some words about the stability of core halo profiles, and if you think there may be plausible in nature when you reach sizes of galaxies?
Okay, so well, this is related to your work, so you
but I would like to
talk
hear
better than me, but yes, I can mention them. And in relation to what I did in the past, so initially I thought that the core halo structures that you found in your models, like that, were corresponding to the curve on the spiral here.
Yeah.
And in that case, we can see that they are unstable. So I concluded that these structures would be thermodynamically unstable. But in your recent work, you found that actually the solution that you found, or some of the or solutions that are similar to the one that you found, could be located just after the turning point of energy, the point B here, and in which case there would be unstable. That would be stable. Sorry.
Stable. Yeah.
So this is interesting because that makes them more astrophysically relevant. We can say that it is really due to the fermionic King model, to the truncation, because if we do the same analysis with respect to this
the box
kind of exactly this kind of caloric curves in the box, we can show that in that case that all the core halo structures that look like the one in your model would be unstable. So it is a bit like a magic but it's very nice that in this caloric curve there are points where the core halo structures would be thermodynamically stable.
Yeah.
At the same time, it's still open. There are still open problems. For example, why does the system will choose this solution instead of maybe the gaseous solution, that maybe the solution 1 that would be maybe more easily to form? And also, we can say that if we are optimistic, we can say that these solutions here, solution 3, are just stable. But if we are pessimistic, we can say that they are almost unstable because they are very close to solution 2 that would be unstable.
Yeah, one comment in that case, Pierre, is that this solution 3 here is the one that matches the boundary, the radius and mass of boundary condition found by constraint for nonlinear structure formation from cosmology, from the when system visualizes, you press checker, when you apply press checker, you can find in a given cosmology the boundary condition for a halo of a given size and mass, and this solution 3 is the one that matches that one. But then we show that there is a family of solutions along this stable branch, which does not necessarily be so close to solution 2. This is important because there is no fight.
So you are saying that solution 3 and solution 2 are very different?
I'm saying that there are families of solutions along the stable branch with larger energy than solution 3, which are also astrophysical and stable. So solution 3 is just in this specific example to match a galaxy of 5×10 to 10 solar masses. But okay. I'm saying that you don't need to be that close. Generally, this is the state.
So you mean that also these solutions here
exactly
are relevant? Okay.
Exactly, many of those.
Okay.
And we can maybe continue the discussion session. Some more.
If you don't mind, I have a question, Carlos.
Yeah, sure, Greg.
Okay, it's related to some different result of Pierre-Henri recently published. There was a claim, kind of proposal that these explosions that you were talking about could be relevant for supernova explosion really observed. So could you please comment on that? What do you find relevant there?
Yeah.
Okay. Well, I'm not so sure because, well, for me, this explosion here is more academic than, well, I'm not sure. But what I want to say that in relation to supernova, that the process of supernova would rather correspond to this collapse here. in the sense that in supernova, there is indeed an explosion, but there is also an implosion. So the collapse would correspond to an implosion, but we can show that the solution that is reached in this very idealized system has a very hot atmosphere, which is held in the present case by the wall of the box. But if we remove the wall of the box, it would be ejected. So what is related to the supernova phenomenon is this type of collapse at some low energy, implying not only a collapse of the core, an implosion, but also an expulsion of the halo, an explosion. I think it is different from this one, which I don't know if they are astrophysical applications, but maybe it's interesting to explore. But actually, in my papers on the supernovae, the process of implosion and explosion is related to this critical energy.
Okay, thank you.
Thank you.
Okay, thanks a lot, Pierre, for the talk. And well, we should move to the next speaker. Jenny, can you start to present? Hello.
Yes, now I can start.
Good.
Okay,
yeah, so
hello.
I'm a bit sorry
now
from the delay in minutes, but as we took some minutes from the discussion session, it will be reduced, so you will have the full 25 minutes. So, well, I present Jenny Wagner from Institute of Theoretical Physics of Heidelberg. She will talk about where my demon hides the emergence of cell-similar cosmic structures. You can start.
Thanks a lot. So from dinosaurs to demons. Welcome to a very diabolic topic. Laplace had a demon who could accurately predict the future. Maxwell had a demon who could order the disorder. And now my little demon here is going to tell you why dark matter halo mass densities seem to conspire to have almost universal profiles. When you take a look from galaxy scale to galaxy cluster scale dark matter halos, they all seem to have a power law type of mass densities. For instance, take a look at the singular isothermal sphere as a very simple example where the three-dimensional mass density is proportional to 1/r squared. We also have some less known profiles like the Moore profile, the Jaffe profile, or the pseudo-isothermal mass distribution, where we all find some kind of combination of power laws. But I'm sure you all know the famous Navarro, Frank, and White profile, where we have a 1/r characteristic in the central part, transiting to a 1/r squared behavior in the intermediate regions, going out to 1/r cubed behavior in the outskirts at the boundary of this dark matter halo shape. Now, when we talk to normal people about dark matter halo shapes, they look a little bit weird because when we cannot directly see dark matter, how do we know all these profiles? And we infer dark matter properties from what I call the cosmic trinity. So first and foremost, we have observations on top. And these observations have provide us with indirect evidence to guide and test our hypotheses. So we get an idea of what is actually there. But the main working horse here is definitely numerical simulations, because numerical simulations provide us with mock observations, which are based on assumed known evolution processes. So numerical simulations can answer the question, how is it possible that our evidence comes about? So we reproduce our evidence with known physics to get to know how this can come about. And I would now like to focus on the third pillar of the cosmic trinity. Namely, I would like to focus on mathematical theory, which hopefully provides us an explanation why these halos look like they are in observations and as well in simulations based on fundamental physical principles. So let's start with simulations. And in simulations, we usually define halos as structures. What is such a structure? It's a description of a static spatial configuration of a bunch of particles. This is a discrete ensemble, but we would now like to infer a mass density, which is a continuous property. So let's assume that the halos are spherical, and then we can take at a certain point in cosmic time, we make a snapshot and we cluster all these particles and we assign these particles to different halos. Then we can say that the mass density of such a halo is given as the mass of one of these particles times the number density of particles at a certain radius. And the number density of particles is the number of particles times the probability density function of one particle to be at a certain radius. So we now have converted this discrete ensemble of particles into some continuous language of mathematics. And this now allows us to interpret the simulations. So we are interested in the slope of these mass density profiles, which is here denoted by gamma, and which is given in this logarithmic form. And we plot gamma with respect to increasing radius from the central part of the halo to the outskirts, to the boundaries of the halo. For instance, take a look at the Aquarius simulation by Navarro et al. When we would like to explain the dark matter profiles by mathematical theory, we need to take a look of what slopes do we expect here and what do we need to reproduce. And this is definitely in the outskirts, a slope of the mass density profiles of about 3 to 4. We need to reproduce this with our mathematical theory because all simulations agree to this. When we go a little bit more inwards, all simulations also agree to have an isothermal intermediate region with gamma equal to 2. There, everything is also quite smooth and clear. But now, when we are approaching the central part of the dark matter halo, we see that this single gamma, they diverge here. And so hopefully our mathematical theory can make a prediction about the power law slope or the slope of the mass density profile in this central part, because this is not conclusively given in simulations. So let's set up the theory as closely as possible to the simulations and what they use as starting points. They usually start with what I call a microscopic ensemble of particles, which consists of NP identically distributed point particles. And usually they are collisionless, meaning they are independent of each other. And because our dark matter halo has a size which is much smaller than the Hubble radius, we can assume that Newtonian gravity is a good approximation for the interaction. And because we are now considering dark matter only, we can also assume that this is the only interaction that we currently have. This is quite fortunate because this allows us to describe as the sum, linear superpositions of pairwise interactions with all the other particles. This is the microscopic ensemble. And what we're interested in now is a macroscopic, coarse-grained halo model, which compresses the entire information of this particle ensemble into a mass density. And this is done by defining the halo as a sphere of a finite radius Rmax. And now we need this probability density function, which is directly proportional to our mass density. And we set it up as Newtonian gravity is a scale-free force obeying a power law profile. We say that this guarantees the ansatz that the probability density function of one particle being at a certain radius is of a power law type. So I have the radius here, and I introduce a scaling radius to make this quantity dimensionless. It's not good for anything else, it's just a scale. Then I define my power law index to be gamma, so the slope of our mass density profile as well. And now comes the trick, the most important thing. The normalization here is done such that I integrate my P over the entire volume of the halo and set this to 1. So the probability of finding one particle, which actually belongs to the halo, should be 100% that I find it in this halo. And this now gives me this normalization constant, which encodes the geometry of the halo, whether it's a sphere or an ellipse or whatever. And it is also dependent on the actual extensions of the halo where I would like my particles to be. And in addition, it also depends, because P is proportional to this power law, it also depends on the power law index gamma. But this is just one lonesome particle. So let's join all the particles together to get a joint probability density function of the entire dark matter halo of all particles together. They are independent, so we can just take the product of all of them to get the joint PDF. In stochastics, it's usually cool to take the logarithm of this, but this is just for the sake of getting simpler calculations. So there's not much physics in there. But the main point now is that we are interested in the most likely configuration of this ensemble, or at least in an extremum configuration of this ensemble. And what is the most important quantity we are interested in? This is the power law index. So we find, or we try to find, the extremum configuration with respect to this power law index gamma. That's what's done in this equation. And when we set in this PDF that I showed you before, and we solve the equation, the logarithm is greatly of help. We find that gamma equals to 2, which comes out due to the dimensionality of our halo being 3-dimensional, plus, and now comes a ratio which encodes the number of particles with which we sample our mass density. And in the denominator is the actual distribution of particles with respect to the maximum extension of our dark matter halo. So this power law index is actually dependent on the quantities of our particle ensemble. This is a little bit mathematic, so let's have a look at the physically relevant cases. We still would like to explain the simulations. So let's jump right into the core of the galaxy, of a dark matter halo. There, the maximum radius is the core radius where our core is supposed to stop. Then we certainly do not encounter many particles there. So the number of particles here will be finite. And then this means that gamma is completely dependent on the actual distribution of particles in this region. So it's clear that simulations cannot arrive at one unique gamma in this region, because it depends on the distribution of very sparsely sampled particles in this region. This explains why we have different gammas for different simulations. But let's assume that on the statistical basis, we find a uniform distribution in this radius here. Then we can insert this uniform distribution, and we find that gamma equals to 1 in this case. And this is exactly the behavior we have for the NFW profile in the core, this 1/r behavior. And this is a special case for the uniform radial distribution of particles there. Now, this is the core. Let's go a little bit outwards. And there, because the radius vastly increases to the intermediate regions, we also find a vast increase in the number of particles that we encounter there. So our sampling gets very, very good. And in the limit of infinitely many particles, we find that gamma equals to 2 in this region. Isn't that great? Because now we have reproduced the isothermal fluid case. And I can also tell you that this is a maximum most likely configuration. So we have explained and reproduced number 2. Now let's take a look at the outskirts. What happens at the outer boundary? We can have 2 choices. The first one is our maximum radius is much larger than the last bound particle in our ensemble. Let's, for the sake of curiosity, take the maximum radius going to infinity. Then we find that gamma equals to 3, which is the behavior in the outskirts of an NFW profile. And what does this physically mean? Physically, we have gravity ranging out to infinity. But our simulation is finite and we have a finite particle ensemble. So we truncate it at a finite radius, much smaller than our interaction range. And that's exactly why we find in galaxy clusters, the largest structures in the universe, why we find this behavior here. And now let's come to exactly the opposite case. When we go to galaxy scales, we have a galaxy, and when we're interested in the surface brightness of this galaxy, we usually take a surface distribution, brightness distribution, and we characterize this in terms of a half light radius. Now let's do exactly the analogous thing for the mass. So let's assume we have a half mass radius here. Then the particle distribution completely spills over our maximum radius. And in this specific case of the half mass radius, we find that gamma now equals to 4. And this means that we have exactly reproduced the behavior of galaxy scale dark matter halos, which is, for instance, found when we assume that the Jaffe profile is the brightness distribution in 2 dimensions, and we extrapolate this to 3 dimensions to get the mass, then this is exactly the behavior here. So taking everything together, we can explain the power law behavior in the outskirts of the simulations and in the intermediate regions. And we find an explanation why we do not agree to a certain gamma in the core. That's the mathematical point in the explanation. Now let me summarize why this all happens in just 2 sentences. So is there a fundamental reason why the profiles should be of a power law type? Yes, there is, because scale-free gravity, with being of a power law type, causes self-similar structures being of a power law type. When we take a look at Newtonian gravity, we have a potential which is of a power law type. We insert this into the Poisson equation and we get again out a mass density which is of a power law type again. But this is just on the basis of mathematics, which works on continuous potentials with on smooth potentials with continuous mass densities. So when we sample this in simulations and in observations, we encounter a finite resolution. And this finite resolution now only allows us to start at a certain minimum radius, because there it's the most, it's the particle that we observed, the first one. And we cannot extrapolate to r equal to 0. There might be demons there. We simply don't know due to our finite resolution. So let's start here. And when we go outwards a little bit, we have a very sparse sampling in this region by a very sparse amount of particles being inhomogeneously and potentially anisotropically distributed. And this causes the power law index to vary between 0 and 2. And we arrive here at 2 in the larger radial regions when we find a homogeneous sampling. So when this halo is sampled very well by the particles. And the outskirts here, they are just caused by the fact that scale-free gravity does not give us a certain radius where to divide our halo into halo and environment. This is completely arbitrary at first. So our choice here, where we choose our max, can determine then the power law index in the outskirts, whether we cut at gamma equal to 2, gamma equal to 3, or even gamma equal to 4. So the entire structures just come about because scale-free gravity causes self-similar structures, and these self-similar continuous structures are sampled by collisionless self-gravitating particles, which is shown in the equation below here. And that's the whole story why power law profiles are important in nature and why we find these different indices for the power laws.
So 3 minutes, Jenny?
Yes, and with this, I would like to thank you for your attention. And if you're interested a little bit more in the physical part of this approach, have a look at my essay, which was honorably mentioned at the Gravity Research Foundation. If you like to see the full equations in detail, have a look at my paper published in General Relativity and Gravitation. If you don't like to read at all, here is a longer talk, including the mathematical details. Thanks.
Okay, thanks a lot, Jenny, for this nice talk and this statistical theory for halos. So does anyone have any question or comment? I have, in the meantime, I have a question, well, more a comment, and then to me, it would be very interesting if you can find, or anyone can find, a kinetic theory in order to an underlying theory of relaxation from which you could obtain some of these most likely phase space distributions where you then use to fit the gamma, because as far as I understand, you can correct me, the initial proposition of this probability distribution you consider Newtonian is with this power law, which is this normalization. Yeah, and then depending on the distributions, on the if it's uniform or not, you can find the different regimes. But it seems that your theory allows more possibilities that they may be realizable in nature from a kinetic theory approach. So it would be very interesting to do this. I don't know if you have some comments on that.
Well, yeah, you're touching a very interesting point. I mean, you say kinetic theory, and at the moment, this is just neglecting any velocity, because when you want to define a density, usually you're interested in spatial positions. And this is why I didn't touch anything about velocities. So I just want to say, let's neglect the velocities because we have cold dark matter. So everything is very slow. And to leading order, we say, okay, we just focus on the spatial positions. And then you can ask, why is this possible? So when does this limit break down? And Binet in 1984, I think, had a paper on that when you have particles which move in an energy conserved orbit, then they spend most of their time in the high potential region, so where the potential is maximum, because the velocity there goes to zero. And so they spend a lot of time in the apex of their trajectory, and they rush through the central part because there their velocity is maximum. And so that's why this works in the first place.
Yeah, so one short comment in the middle. Yes, no, in that case, yeah, I agree, because it is already, you are talking, sorry, you can hear me?
Yeah.
Sorry. No, and that's because you already are considering a relaxed system, and you are saying the kinematics, the particle stays in this orbit, this fixed potential.
This is what you get when you take the maximum likely configuration.
Yeah.
This is the equilibrium, so-called long stable.
Exactly, but my question was more related to to nonlinear structure formation, in a sense, how you get this distribution from prior to self-gravity, meaning, for example, an example is this. I know one example is, for example, the Lindenbell theory of violent relaxation, or the generalization that Pierre-Henri have done, that can show that starting from a Blasov-Poisson, so fully time dependent, you go to coarse grain and you obtain similar equation to Fokker-Planck, but for fermions, and then by maximization principles, you can obtain a most likely distribution function stationary. But so in this sense, it's nice because you can link the fine grain fluctuations, then coarse graining, and then to a most likely distribution function. So in this sense, I was saying that it would be nice to constrain even more your theory if you can have some kinetic theory to work out and see which most likely distribution function within your approach
Yeah, I mean, including the velocities is work in progress.
Okay.
But I'm wondering, when we take a look at all the halos in the relaxed state, they seem to have forgotten their merger history. And there are a lot of simulation papers showing that they end up in a like self-similar state. So they do not know how many mergers they had, and they forget their merger history. And so I was wondering in how far we could just treat this final state as independent of the history, because in the end, the final state does not depend on the history. It seems to be some kind of attractor in this phase space.
Yes, it seems that, yes, it's an interesting point. It seems that the subsequent violent relaxation at its merger, it kind of erased the memory of what was happening. And then, yeah, yes. Then another interesting, well, sorry, I will just say that we now move to the discussion session.
Carlos, if I may, another short question.
Oh, yes, Gregory.
Gregory speaking, Gregory Michel. I'm sorry, just, well, probably this could be discussed further, but just to ask it, you know, the probability distribution, Jenny, you are assuming a power law, right? This is okay for gravity when you have, in principle, a few particles, but actually, I guess in a strongly correlated system such as halo formed, okay, there is no anymore simple power law. And just to give you a counterexample, you have expanding universe, for example, self-gravitating system there. So you can show that the correlation present there will be similar to the Debye type correlation. Okay, and then you don't have just a power law, you will have exponential cutoff somewhere. So something similar, very likely, will set you a scale in this system of self-gravitating system we are considering. Would you comment on this briefly?
Yeah, I mean, this depends on what else you are considering. At the moment, I'm just considering self-gravitating systems without any further scaling, and self-gravitating systems are scale-free, so I do not have a scale. But as soon as you introduce velocity or a cosmological background which expands, of course, you will get a scale by the counterbalancing of gravity with velocity or with something else. I also expect for baryonic interactions, you also have the electromagnetic force, or you even have the kinetic energy by the particles. And I also expect some scale arising there. Maybe this then gives us a preferred scale where to cut halos into halo and backgrounds. And then, of course, you might get additional deviations from the power law. I mean, at the moment, the particles are even independent. If I introduce collisions, then the whole story will change, because you also have the particle interactions due to the collisions. But there were some papers by Ellis et al. In the 70s and 80s, and they had a very, very general formalism based on the Boltzmann equation plus the Einstein field equations, where they had a particle ensemble, and they found out that even with collisions, you can reproduce under the conditions of isotropy of your fluid. You can even get exactly the same stuff out as I do.
You can or cannot?
You can under certain conditions, and this was really marvelous because it's the generalization of my approach.
Yes, but yes, one comment. I know, Gregory, if you want to comment again, but I have a comment. Okay, thank you. I have a comment also related with the Gregory's comment, which I fully agree with that. In astrophysical systems, at some point the power law should break, and you have either exponential or polytropic like cutoff. And one way, that's why it's related also to my question of kinetic theories, because kinetic theories of violent relaxation with maximization entropy leads naturally to evaporation of particles and with a cutoff in the energy in the most likely distribution function. So yeah, this for example will put an extra factor maybe in your probability that says that the trend is not just power law, but or is power law, but in a very short window of radii, and then go. Yes.
I was wondering, where do you then get the cutoff from? I mean, you can assume something like a Yukawa potential, which gives you an exponential decay in the outskirts, or?
No, you can check. The beauty of this is just you can check this paper of Chavani. He showed that starting from only by having Blasso-Poisson, either in general relativity or in Newton. So in general relativity is not called Blasso-Poisson, it's called Einstein-Blasso, of course. But either general relativistic or Newtonian, with this maximization entropy, starting from a Lindenberg-like entropy, which is the one that not only considers the system, but also the environment, this mixture. And he showed, you can see that from this maximization, the most likely distribution function is of Fermi Dirac type with cutoff. I mean, maybe it sounds a bit magic, but this is in the demonstration, the mathematical procedure of this maximization, that you can end up with this cutoff. And so you have to go through the calculation, but maybe the physical meaning of that is just that at coarse grain level, which is the most likely distribution function you are finding, is that you have a diffusion current, effective diffusion current in this approach, which says to you that you are evaporating particles. And if you are evaporating particles, you need at some point to have a cutoff in energy, after which you have no more particles. And it will be the reasoning, more or less. But yes, if you do not consider J equals 0, current equals 0, you end up with Lindenberg traditional distribution function, which is scale-free and goes with a slope -2, which we know is not much astrophysical, as you said, because you need powers -3 or -4 at some point.
I was wondering, another question back, when I saw these entropy maximization techniques, they usually are based on phase space. So you chop your phase space into some parts, so for the coarse graining, and then you assume that you have a uniform distribution in phase space as soon as you reach the maximum entropy level. And
uniform? What do you mean uniform?
Yes. You assume that you have the least amount of information, which is a uniform distribution in phase space, which then gives you the maximum entropy, so the maximum not knowledge.
Uniform distribution, but it's not uniform. You mean it's not homogeneous? I don't know.
No, I mean, when you take a look at the phase space distribution and you maximize the entropy, then what's the state where you have the least information? Because this is the state of the maximum entropy.
Yes.
And this usually means that every state is equally likely.
Yeah.
Yeah, so this is what I mean by uniform distribution.
Okay.
But the problem here is that you are searching for this maximum entropy state in your phase space, and usually you need to assume some conservation laws as well in order to use this. For instance, when you determine the mass density from the velocities, from the rotation curves, then you translate the velocities into the positions, and this gives you then the mass density by means of the energy conservation.
Yeah.
And is it clear that we really have energy conservation here?
Well, no, of course, this is a good question. And another good question is if you really reach a coarse-grained entropy maximization. Exactly, these are two important questions to be answered. I mean, but I mean, I like to put all the things at the same on the table, because this is one point important to discuss. But another point is, because you would like to know if reality goes tending to these maximizations, but also important to answer is if embodied simulations, how much you can trust in the last state of embodied simulations, because I mean it's not clear if there are many things not clear. For example, the inner parts of the distribution, you have to tune your because they work on with classical particles, you have to tune with this
convergence radius.
Which is related to the fine tuning of that, because you want to get rid of the infinity of the gravitational force
Yes, so you have this little smoothing epsilon so that you do not get the collisions. That's what
exactly
what they do with collisionless particles.
Yes, and this leads to effective or trends on the distribution towards the center, which has been shown recently in some papers that if you relax this condition, which is how to say more technical and numerically to solve this tension of self-gravity at that scale, is you can obtain cores averaged. Of course, the solution there oscillate because the resolution is not good, but it was a paper showing that indeed cores may not be completely are already there in the simulations, but if you use this tuning of the small scale, you finally end up with this Cusp at some point. But so this is not clear these points, but also are not clear what happens with the coarse grain entropy in simulations. Yes, and also it's not clear fully the virialization, because they in order to stop and say you have a halo, as far as I understand, they use a virial condition that has to be fulfilled by the particles in average. I mean, and then there are all these things that have to be put together.
I mean, the virial condition is not a very stable condition because it depends on the statistics of the particles.
Yes. Yeah.
But as far as I know, they use a friend of friends algorithm where they just have the that the intermediate distance to the next particle needs to be smaller than a certain threshold, and then they count the particle still to the halo, or they just take it to the environment.
Yeah. Yeah, because as you know, simulation also, as you said, always finish with a power law, and because at some point your density is below critical density or environment density that you just forget about, but you see that there is no clear prescription of how the system stays stable and a finite mass. Because you cannot have access to the equation of states, you don't know what happens towards the center to maintain this stable. Don't know what is the, I don't know. To me, there are many open things or questions in n-body simulations, and I think it's very interesting to keep working on searching which approach is more close to astrophysical reality. If thermodynamics, which we know is with demons and very. It's a very fundamental approach, or we have to, I mean, there are competing, I will say there is competing theories. Of course, n-body has the power to cover many redshifts, which is the beauty. But yeah, let's see, to me, it's still open, which is the last state, the most likely state at relaxation related to halos.
I mean, the other point in simulations that I found a bit weird, they're asking what is the density in core, but actually they define their core around the most bound particle delta distribution with the mass of this single particle where the halo is centered on.
Sorry, could you repeat the last? I lost connection.
The most centered particle is usually the center of a dark matter halo in a simulation. And so you could say that the central part of a halo is a delta distribution with the mass of this particle. And then the entire halo is more of a correlation function. How likely is it to find another particle, a third particle around this most bound particle?
You mean that the delta, but from where it arises, this delta in the approach?
Yeah, it's a point particle, so you can also take. I just wanted to say that it's a point particle in the center. So
yeah, it's a pixel. It's a non-resolved pixel. So you could,
right. Right.
Yes. Yeah, and also this leads to, now we were talking about the central region, or because many people extrapolates the profiles. To me, another and still unsolved and very important topic is how dark matter behaves around supermassive black holes. If you, I mean, people use some extrapolation with this so-called spikes, but the problem is that there are two things. I mean, one point is that you don't know how much you can trust in this extrapolation. First, and second, is not, of course, it's not stable. This because the black hole is a sink, and then you should first solve the Euler-Einstein solution for particles to show if this is the time scales of the system, because for sure it's not fully stationary. You have to first demonstrate if this lives long enough in this steady state of profile to say, okay, I can use that. People is using this without taking care of that, and to me this is an ill-defined problem. And also, yeah, and also the fact that they don't have the equation of state to see, you know, many issues there.
To begin with, yes. I mean,
Yes.
that's why I based my density not on any kinematical properties or pressure properties or whatever, because we are lacking this information.
Yeah, yours is more, it's general, probabilistic, yes. And sorry, and now, sorry, Rodrigo, sorry, can you please?
Yeah, so I'm really enjoying this discussion. I was just wondering, regarding your earlier point, whether people have tried looking at the density profiles, but by essentially centering using, you know, a much larger view. So essentially using the I don't know, an intermediate distance in order to pinpoint the center of the halo, rather than just the, you know, the location of the densest point.
So you mean centering the halo on other salient features of the halo?
Well, just I mean, you could imagine doing it on, you know, every single using all particles, right? But probably that would you get unstuck there because of you know, the galaxies nearby and so on, your subhalos, your halos nearby. But you could imagine doing that at I don't know, around the scale radius or something like that.
I think this is done, and it's so you start like from seeding single particles. You take the pairwise potentials, and then you extend this to a kind of like watershed algorithm, where you then end up in having different trunks of dark matter halo potentials, and then you need to see whether you are just in a subhalo or whether there's a bigger halo underneath it. I mean, this is like how you grow the halos in the simulations.
And so then, so my question is then, does that then change the central profile that you find?
This I don't know, actually. I'm sorry.
Thanks.
Okay, thanks, Rodrigo.
I have probably used a certain fraction of the bound particles as well to measure the center of the dark matter halo.
What did you say, Druva? Sorry.
So regarding the discussion we were having about the center, like what Rodrigo was saying, that instead of using the most bound particle, if you use a collection of the particles to define the center. So I think I have seen, I have to look into references, but I think people have used a certain fraction of the bound particles, say like 5% of the most bound particles or 10% of the most bound particles, something like that, to define the center. And I'm not exactly sure how sensitive the density profile is.
Yeah, but in any case, given that the cosmological resolution, even the real refined this cosmological simulation, these distances are huge, astronomically speaking. So speaking about the center still is, in these cases, even if they apply a criterion, I don't know what we are talking about, maybe, I don't know, 10 kiloparsec or 100 parsecs, I don't know.
Mm-hmm.
So this would give you a less precise center in that case.
Okay, I have another question, Jenny, which I wanted to make before and I didn't. So you show that you can find a distribution of particles n such that you recover the R2 minus 1 slope in the inner region, right? Similar to NFW. So the question is there any, or have you found another possibility for n such that the slope towards the center is close to 0, near, similar to Barkert or Coren-Nasto?
Yeah, so if you, I think the very trivial solution is when you have a very sparse sample of particles, and when you just have one particle there, then you have a constant density, namely the one of this particle. So you will have gamma equal to 0 in that case.
Yeah.
And that's
constant, n equal a constant, you say? No.
Yes. So the number of particles is just one. And I mean, that's what I think exactly is going on here, why you have this runaway solution in the Aquarius simulation. Because what you do here is you increase your resolution towards the center, and these simulations here are just simulations with increasing resolution. And you see that when you increase the resolution, that you get further and further towards a constant density, like gamma equal to 0 here. But I think all you're doing here is you are chopping the first bin you have, where you average over all the particles to get your mass density in this first bin. And now imagine your first bin just contains one of these particles, and the convergence radius here approaches exactly this first bin. And so the constant density here, I think, is unavoidable. We run with our convergence radius, which is usually much larger than the first bin width. We now run with increasing resolution to this first bin. And in the first bin, we have this constant density because we need to start from something. The numerical simulations have this resolution, which gives us this constant at the start. And I think that's what's happening here. And I talked to someone in the collaboration, and he also said, yes, this seems reasonable.
So there is also a possibility within this approach to reproduce this cores.
Yes. I mean, naturally, because it's the finite resolution of the simulations. I'm just trying to stay with the simulations and say there is a finite resolution, so I need to start from R min larger than 0. And I do not make any assumptions in any interpolations to the central core.
Yeah. So I know someone else has a question. My humble suggestion, because maybe to improve, or you're probably considering already, is to try to link with kinetic theory to see which distribution is more likely than the others. And another is if it may be the possibility to include the quantum nature of the particle somehow effectively in your distribution. This would be very nice, either because it may lead the possibility to link with, for example, the fuzzy, the boson case of dark matter, or either fermion. So it's good. Interesting.
Thanks a lot. This would be highly interesting. And thanks a lot for the great discussion.
Okay.
It was marvelous.
Okay. Thanks all of you for participating and for the nice discussions and talks. And hope to see you tomorrow. And Rodrigo will start tomorrow, right?
That's right. Yeah.
Good. Okay, people. Thanks a lot.
Thank you.
Thanks. Bye.
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 Thank you. Bye.